All right, let's just jump right in. I want you to imagine for a second that you're a detective, but your crime scene, well, it's microscopic. You've got some kind of unknown substance, a mystery compound, and your job is to figure out exactly what it is. Problem is, you can't see its structure, not with the naked eye. So where do you even start?
That right there, that's the big question, isn't it? It's the central mystery we're going to try to solve today. Think of this as a molecular detective story. Our prime suspect is a molecule, and we need to gather all the clues, analyze the evidence, and crack its identity. But, what kind of tools do you even use when your suspect is smaller than a single speck of dust?
Well, meet your forensic kit, spectroscopy. Basically, it's the science of shining light on our molecular suspect and just watching to see how it reacts. See, different kinds of light interact with the molecule in totally different ways, and every single one of those interactions leaves a clue. It's a piece of evidence that helps us build a complete profile of what we're looking at.
So our first tool out of the kit is going to be UV/visible spectroscopy. The best way to think about this one is that we're following the electron trail. We're going to hit our molecule with some ultraviolet and visible light and carefully watch how its electrons behave. And trust me, this first step can give us some pretty major leads right off the bat.
Now here's a crucial point. Not every part of a molecule is going to care about UV-vis light. We're looking for something really specific, a structural feature called a chromophore. Usually, these are systems with things like pi bonds or non-bonding orbitals. This is the part of the molecule that actually absorbs the light energy. It acts like its most distinguishing feature, like a tattoo or a scar on a suspect. So what happens when we hit this chromophore with light? Well, when it absorbs that light energy, its electrons get this sudden, massive jolt. They get super excited and literally jump from their home base, their ground state orbital, to a higher empty energy level. And it's that jump, that electronic transition, that we can actually measure. That's the basis of our very first clue.
But, this evidence isn't always straightforward. The exact wavelength the molecule absorbs can actually be influenced by its environment, like what kind of solvent it's in. If the absorption shifts to a longer, lower energy wavelength, we call that a bathochromic shift, or a redshift. And if it shifts to a shorter, higher energy wavelength, that's a hypochromic or blue shift. Analyzing these little shifts gives us vital clues about how our chromophore is interacting with everything around it.
And it's not just about where the absorption happens, it's about how strong it is. The intensity can change too. If we see an increase in that absorption intensity, that's called a hyperchromic effect. A decrease? That's a hypochromic effect. It's kind of like our evidence is suddenly getting louder or quieter, giving us even more detail about our molecule's structure. So, these electron jumps we're detecting, we can actually sort them into different categories to get even more specific info, especially when we're dealing with transition metal complexes. We can see things like DD transitions happening right inside the metal's own orbitals, or charge transfer transitions between the metal and its partners, the ligands. We can even see transitions happening on the ligands themselves. Each type reveals a totally different piece of the puzzle. Okay, let's zoom in on that transition. This is like an inside job. It happens right within the metal ion itself. See, in a complex, the metal's d orbitals aren't all at the same energy level anymore. They get split by the ligands around them. So when light with just the right amount of energy comes along, an electron absorbs it and gets promoted from one of those lower d orbitals to a higher one. The energy of that jump tells us directly about the crystal field splitting for that specific metal. Super useful stuff. Then there's charge transfer. This is a totally different game. Here, an electron actually moves between the metal and its ligands. It could go from the metal to the ligand, that's MLCT, or from the ligand to the metal, which we call LMCT. These transitions are usually incredibly intense, way stronger than DD transitions, and they give us some killer information about the bonding going on between the metal and its ligand. All right, so we've followed the electron trail, we've got some good leads. Now it's time to pull out our second tool, infrared or IR spectroscopy. If UV/Vis gave us sort of a general description of our suspect, IR is about to give us the molecule's unique, undeniable fingerprint. So here's the fundamental idea you gotta get. Molecules are not these rigid, static little things. They are constantly moving. The bonds holding the atoms together, they're like tiny little springs that are always stretching, bending, and vibrating. IR spectroscopy works by measuring the exact amount of energy it takes to excite all these different vibrations.
And these vibrations, they come in a few different flavors. You've got stretching, which changes the length of the bond, and bending, which changes the angle between bonds. And the bending motions even have these great descriptive names, like scissoring, rocking, wagging, and twisting. Every single one of these normal vibrations for any given bond needs a very specific amount of energy to get it going, and that's what IR is so good at detecting.
So when we get our IR spectrum back, which is basically our fingerprint report, the most important signals we're looking for are called the fundamental bands. These are almost always the strongest, most obvious signals, and they correspond to the simplest jump from the ground vibrational state to the first excited one. These are the big, clear lines in the fingerprint that we look for right away.
But hey, sometimes we get a little bonus information. Weaker signals can also pop up, things called overtones, which are like bigger jumps to higher vibrational states, or combination bands, where two vibrations get excited at once. You can think of these as the faint swirls and ridges in the fingerprint. They might be a bit harder to spot, but they add this whole other layer of detail and confirmation to our analysis. So what decides how fast a bond vibrates? Well, it's a lot like a simple spring, and it really comes down to two main things. First, bond strength. A stronger bond, like a triple bond versus a single bond, is like a stiffer spring. It's going to vibrate at a much higher frequency. The second thing is the mass of the atoms on either end of the bond. Just like putting heavier weights on a spring slows it down, having heavier atoms on a bond makes it vibrate at a lower frequency. It's that simple.
Okay, we have gathered our evidence, we've got the electron trail from our UV/Vis analysis, and we have that unique vibrational fingerprint from the IR scan. Now it's time for the best part. We put it all together, see how the clues line up, and finally, we crack the case.
So what's the bottom line here? After all this technical work, what does this pile of evidence actually tell our molecular detective about the identity of our unknown suspect?
Well, it gives us a complete picture. UV spectroscopy gives us a partial ID. It tells us about the overall electron system, if there's any conjugation going on, maybe how a metal is interacting with its ligands. But IR spectroscopy, that gives us the unique fingerprint. It tells us with near certainty, yep, there's a carbonyl group right there, or that's definitely an OH bond. When you put them together, there's really no room left for doubt.
You see, in the end, all these squiggly lines on a chart, they aren't just random data. Every single spectrum tells a story. It's a story about a molecule's structure, its bonds, its entire environment. The real skill of a chemist is just learning how to read that story. It's about becoming fluent in the language of the molecules themselves.